Hello and welcome to the web series ZeroPM Pieces. In the ZeroPM Pieces, the researchers in the project will tell you about one piece of the ZeroPM puzzle that they're working on. So without further ado, here comes a ZeroPM piece.
Hello everyone, my name is Amanda Rensmo and I'm a PhD student at Stockholm University, and this presentation will be about my first PhD project, which is about defining uses of PFAS in green energy technologies. And the concept of green energy, I'm sure you've heard about. It is that we want to move away from fossil fuels and have renewables instead, such as wind and solar. But this also means a change in the system of the energy system. So that requires more batteries that can store this energy that can then be used in sectors such as the transport sector and others. And I just like to note that in my presentation, I have not assessed the greenness of these technologies, just adopted this concept. And I will focus mostly on the two on the bottom, so batteries, and also a little about wind. And when it comes to the green energy sector, we've heard the statement that PFAS are essential for the green energy transition. This can be exemplified here, where they link green transition to lithium-ion batteries, and therefore, since batteries require PFAS, then PFAS are essential for green transition. And similarly here with fluoropolymers linked both to lithium-ion batteries and wind turbines. And these excerpts are from comments in the Universal PFAS Restriction Proposal consultation. So this regulation or restriction came about in 2023. Opening up to a public consultation, and it's an ongoing process within the EU to restrict uses of PFAS. And PFAS, I don't think I need to explain in too much detail to this audience, but just to set the scene, PFAS are any substance with CF2 or CF3 in the structure, as described by OECD. And in the restriction proposal, they link it to the very persistent feature of PFAS, either on their own or their terminal degradation product. But they also link to additional concerns such as ecotoxicity and effects on human health. And if we discuss PFAS in the green energy transition, we in our work had the hypothesis that there are several potential uses of PFAS in green energy technologies that either are only claimed as potentially useful rather than established on the market, or already have technically feasible alternatives on the market. And I'll mostly talk about batteries today, so let's go into it. Batteries, as I said, they're used to store energy from wind and solar, and that could be in big battery parks. They're also used in other applications or end-use applications, such as electric vehicles, as well as consumer products and many more. And this means that they have a complexity on their own, but also a large diversity on where they are used. And therefore, battery manufacturers develop a set of requirements or develop to a set of requirements for the end-use application. And to recognize this complexity, we had developed a methodology in 2 stages. And the first stage is where we took comments in this Universal PFAS Restriction Proposal public consultation. There were more than 5,600. And we assessed any mention of batteries and PFAS connected to each other in these. And we then incorporated this into a battery use level framework, making up a database of records of potential PFAS uses. And from these, we assessed if there was sufficient information available, meaning that we could then list them as potential PFAS uses. And this resulted in 341 records in our database. And of these, 86 had sufficient information. But since there were a few duplicates or details only that differed, this resulted in 38 potential uses to be listed. And here you can see that I've used words such as potential and records. And this is to reflect that we don't consider a use to be confirmed only because it's mentioned once by these in the technical documentation. But we really want to assess what is available on the market. So therefore, in the second stage, we took this list of potential PFAS uses in batteries and tried to confirm or contradict this using supporting evidence. And these are 4 different types that I'll explain later on. And from the confirmed potential PFAS uses, or I guess then it wouldn't be potential yet, or still it'd just be the PFAS use, we would then try to identify potential alternatives. And then we would use, again, this supporting evidence, the 4 types, plus also what was described in the consultation comments. And I'll already, I guess a spoiler alert, I'll already describe what we found. And we found 18 potential uses could be confirmed and 2 could be contradicted. And we could not assess, due to lack of information, 18 potential uses. And from these confirmed potential uses, we could identify 11 that had potential alternatives in varying degree. So this was the overview of the methodology. And this methodology highly depends on the battery use level framework. And I'll try to describe it a little more in detail now. So we first have the battery. And I'm sure you've all of you seen an alkaline battery, which is these that you have in a TV remote or bicycle light or similar consumer products, as well as lithium-ion batteries that are in electric vehicles or in cell phones. But there is a big universe of different battery types, or should I say technologies, and many more than I have listed here. So therefore, we take all of these and see, can we list this as a potential PFAS use based on this information? And we recognize here the complexity of batteries and note that batteries are complex objects, meaning they're made up of several components. So we went into the component level, the simple article, and here it's illustrated with a washer, something that you have on a screw to, for example, insulate electrically or mechanically or similar. And this component could be, for a battery, it could be a washer, but there's also others that were listed, gasket, casing, as well as these that are cell-specific that are mostly linked to batteries, such as cathode, electrolyte, and anode. So then the question is, can we now determine if it's PFAS that is used here? And this is the level that we want to assess. But we want to link the two. And this is not a direct correlation, or there is a big gap, I would say, between the component and the battery technology level. And I explain shortly how we try to close this gap. I'd also first like to note, if we go upwards instead, towards the application, you can have, like I said, batteries in a lot of different applications, medical and consumer products. And in this work, we haven't gone in this direction because we recognize there is not a one-to-one connection with, for example, which battery you have in an electric toothbrush or other applications. But this will be future work. So now this slide becomes a little messy, so let's clean it up a little. And now I will go into this gap between the component and battery technology. So between them, we would assess different types of information depending on what type of component it is. And I most easily explain this with examples. So if we have a cathode, we would need to know the chemistry, meaning the type of cathode that is used in this lithium-ion battery. And there are a large variety on the market, and there are a lot of acronyms for this. I will keep to the acronyms because for the purpose of this talk, we're not going into detail, but I can, for example, say that LFP stands for lithium iron phosphate, and that is the where the electrical energy is really obtained. We also look into the electrolyte. Then it's really not the chemistry that matters. Then it's the electrolyte phase, which is either liquid, most common, but it could also be semi-solid or solid electrolyte. But for other components, like the washer that we see here illustrated, then it doesn't depend on the chemistry or the electrolyte, but it depends on where it is used in the battery. And a battery in most application is not only the cell that we can see here, but the cell makes up module, which then together makes up a pack. And this is what we have, for example, in a electric vehicle. So these are different types of units, and it's important for understanding where the washer is used to know which unit it is. So now I've explained the battery use level framework, as well as the availability of information. We would need to know all of these two levels, the battery component, the battery technology, and this intermediate step to be able to list it as a potential PFAS use. And we also, I should say, in the battery use level framework, or in the database, include substance information, if it's a fluoropolymer, or if it's even stated which fluoropolymer, or if it's only noted as PFAS or non-polymeric and so on, as well as any information that were about the function. But this I will not describe today. And this all, as I said before, comes to 38 potential uses. And this is, I would like to exemplify with the list of those that are relevant for lithium-ion batteries. And there you can see here. And we have several different types of cathodes where a PFAS use have been listed, but also in the non-cell specific ones, like the 3 on the bottom. So from these potential uses, as I mentioned in the beginning, we had the second stage where we confirmed or contradicted them. And here I have 4 different examples on the supporting evidence, and I will explain them a little further. So we first looked into previous use mapping studies. It's example, the Universal PFAS Restriction Proposal in itself, as well as the Gluge et al. Article, but also other reports from NGOs or others such as governmental agencies about anything related to uses that are about PFAS and batteries. And then we also reached out to battery stakeholders, leading up to 11 interviews, semi-structured interviews, which are then included into the assessment. Teardown analysis studies is where we look into if in the battery field there is a subfield where they buy batteries and then tear them apart and analyze the material composition as well as other things. And this is very interesting to see that they have actually seen PVDF, for example, in the battery cathode or lithium-ion battery cathode in a specific model of a certain brand. And lastly, the battery field in itself is huge. So there are many literature reviews on this in this field, and we selected just a few cases to learn more about the functions and substances and also other relevant aspects. So now I'll go into the second stage and what we found for lithium-ion batteries. So we evaluated these 15 potential uses to see if we could confirm or contradict. And we have a scale ranging from 1 to 5. And then 6 means lack of supporting evidence. So it could not be concluded or contradicted. And this list we then added into a matrix. As I said, this the information relates to which part of the battery it is. So you can see here, for example, in the cathode, different types of chemistries. It's very likely that they use PFAS, and here as a binder, most likely PVDF. It could also be TFE. Whereas if we see on the anode side that it's very unlikely to be a PFAS use. And I'd like to remind you that what I have here in this matrix is those that were listed as potential uses, but we could hereby contradict them and see that they're not uses on the market. And then lastly, looking into the alternatives, and then you can see the scale changing here on the side from no potential alternatives to most or all that have on the market potential alternatives. And I'd like to focus your attention on the cathode general binder when I switch here, and you can see that it turns from red to more yellow or green, meaning that there are either one or several potential alternatives identified, and then these we refer to on the market, and those are the proxy for technical feasibility, so not lab scale alternatives here. And this particular one, LFP, that is in light green, that is because it's not sensitive to water, opening up a wider range of alternatives. And then just shortly, I'll describe the second case, which is wind turbines. And this is preliminary results as of now. And here we noted the potential use of wind turbine blade coatings, of course, in a different framework. And the supporting evidence show that there are several different alternatives to this, and these are already provided by coating companies, as well as the Wind Europe, the industry organization, describing that it's they're already using PFAS-free coatings. Again, I'd like to highlight that this is preliminary results, but this is also a case of where we could contradict a potential PFAS use already before going into the alternatives assessment part. So going back to the hypothesis again, and this time I will explain it just for batteries. And if we look at the number 1, on if they are claimed potentially useful, then we, as I said, noted 2 potential uses that were contradicted in this second stage. And then in terms of alternatives, we identified 11 confirmed uses that then also had potential alternatives in a range of technology readiness level. And also, since we couldn't assess 18, these could either go into some of these categories or could be a confirmed use, but we don't know. So key messages today is that batteries are complex objects. So that means we need to look into detail to find uses for which there are technically feasible alternatives, going through this methodology that I explained today. But I also want to note that it doesn't mean that they can be substituted from one day to another. There are other aspects such as processes and infrastructure in battery manufacturing. And also that, as I explained before, we didn't look further towards the application or end use. And this will be a future work of us. This means that we cannot say today if all technical requirements will be fulfilled for these listed potential alternatives. And also noting that potential alternatives refer to that we haven't assessed how hazardous they are. And with that, I'd like to thank my supervisor and also co-authors and colleagues at Stockholm University, particularly also those which I have interviewed, and many more. Thank you.
ZeroPM, Zero Pollution of Persistent and Mobile Substances. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under grant agreement number 101036756.